Hey everyone, welcome to another video in our congruence transformations series. Now, we're going to take a little bit of a detour just to talk about an extension topic. So something that we're going to touch on a lot more in this series next year. And this is the idea of similarities and similar figures. So hopefully, I'll be really brief here. I don't want to overload you guys just yet, hit you with questions, anything like that. I just want to give you a gentle introduction into the idea of similarity. What do we mean by similar figures? What makes two figures similar? And we'll end it there. Now, I asked a question at the end of the previous video, or towards the end of the previous video. When talking about congruent triangles, I said, oops, why isn't angle, angle, angle enough to prove congruence? And I got you to have a think about this. Now, whether you have or not, that's okay. It's a bit of a hard thing to consider initially, but this idea of angle, angle, angle for congruent triangles, for example, we said that the main idea to say something is congruent is that it is identical in every way. Now, can we have, let's say, a triangle with all equal angles? So we have this angle, this one, and this one, all equal, all because it has the same angle values as another triangle. Well, it's not necessarily going to be congruent because think about triangles in general. No matter what shape or size, what do all of their angles add up to? Well, they always add up to 180 degrees. Whether we make the triangle bigger or smaller, the angle size is preserved. So if I draw a bigger triangle, just enlarging the one I've currently drawn, and I have the exact same angle markings, I can have this. I can get a bigger triangle with the exact same angles. The reason this doesn't work for congruence, the reason we always needed at least one side, remember in all of the proofs, even angle side, we needed one side. That side being equal gave us a sense of scale. That told us, well, okay, these are the same because the angles are the same. So the corresponding sides to those angles are the same. But we needed to know that at least one of those pairs of sides were equal because that gave us a sense of the scale of the triangle, how big the triangle is. And if they have these same angles, but are different sizes, these are no longer congruent. These are what we call similar triangles. Similar triangles or similar figures. Now, these ones here, they are the same. So they're the same in a sense where they have the same shape. You can see these two that I've drawn here. They do resemble one another, but they're not identical, right? One is bigger than the other. So to define similarity, similar triangles, these, well, for one, they look similar. So have a similar shape. So that means equal angles. but have a different size. I'll keep the definition quite simple for now. There's more to it later on, which we'll get into next year. But let's think about, well, what makes these two similar? Well, you may notice, and I don't know if I've drawn it well enough, but you should be able to see roughly that all of the sides seem like they're in proportion to one another. Although one is bigger than the other, it appears as though they've all been scaled up, they've been increased by the same amount. Now, this goes for any type of shape, right? We've been talking a lot about triangles. Let's talk about quadrilaterals. Now, a quadrilateral here all quadrilaterals have an angle sum of 360 degrees, but we know that we can have ones that are bigger than others. We can look outside in nature and look at the rectangles we see. We know we can have rectangles that are different sizes. What actually makes them similar? Well, I've drawn this one here, and I'm going to draw one that is bigger, and I'm going to see if you guys can pick up on what's so special about this bigger one. How does it relate to the smaller one? Have this one here, and I'm just being careful to count. Okay, here and here. Sorry for the bad drawing, but these are an example of similar triangles. Now, I want to consider, similar figures, similar quadrilaterals, because any shapes can be similar. They have to have the same shape, and their sizes have to be roughly in proportion. Now, we're going to talk about this now. What have I done to make this triangle on the left into a bigger one with the same shape? Well, let's actually look through, and I've done this on the grid line on purpose. I want to look and measure, well, how many units of length are each of my sides? Well, this is a rectangle, so the opposite sides are going to be equal. So I'm going to write a couple of dimensions on here. I can see that when I measure along my grid lines, I go 1, 2, 3 along here in the horizontal direction. So this thing is 3 units long. And let's look at this one here. That's 1, 2 little grid markings high. So this is 2 units up. And I'm now going to measure how big these ones are. So let's say this one as well as this side of my rectangle. Now, I should say as well, these all have 90-degree angles for rectangles. We've covered this before. And all of our angle sums in our quadrilaterals, specifically rectangles as well, add up to 360 degrees. Now let's count how long these same two dimensions are on my bigger shape. So 1, 2, 3, 4, 5. Whoops. 1, 2, 3, 4, 5, 6 across. So this distance here is 6 units. And let's measure my other length. So that's 1, 2, 3, 4. Okay, so that's 4 units in height here. Now, I want you guys to think, what have I done in order to enlarge my rectangle on the left? What have I actually done here? Well, let's look at a relationship between the numbers, right? How can I make 6 from 3 here? Well, I can get 6 from 3 by multiplying 3 by 2. Okay, that's something. What about the relationship between 4 and 2? Well, 4 is 2 times greater than 2. So in getting from this smaller one to my bigger one, I have enlarged it by a factor of 2. To get from the smaller to the bigger, all of the sizes here are in proportion. And it's the same as the remaining sides. This is a length of 4, this is a length of 2. This is a length of 6, this is a length of 3. So to say figures are similar, so in proportion, same shape roughly, but not congruent, instead similar, all of the sizes have to be enlarged by what we call a scale factor. Now think of this as the 2 times zoom on your camera, for example. You take a photo of, I don't know, a car, and you do a 2 times zoom. Everything you see on that car is going to get bigger on your actual camera screen. That is an application of similar figures. So I'm going to write down here, for figures to be similar, for 2 figures to be similar, they need to have all sides enlarged by the same scale factor. So what I mean by that is that, and they're also going to have, I should say, will also have equal corresponding angles. That's another note for these things here. But the criteria for us to say that, okay, this rectangle on the right is similar to the one on the left, we need to find a number that all of the sides have been scaled by. So a number multiplied to each of the sides here to make each of the sides here. And we found that in this little investigation, we found that each was multiplied by 2. This thing here, my number 2, is my scale factor. The number that was applied to each of the dimensions in order to enlarge it. Now, we're going to stop here because we're going to get into this in a lot more detail in the next series, and I want to give myself enough to talk about in that following series as it relates to similarity. But thank you so much for watching, guys. This is how we can distinguish similarity from this idea of congruence, from this idea of things being identical in every way. It's in the wording, right? You can see these 2 rectangles, they are not identical. If we wanted to describe this, we know for sure they're not identical, but they look pretty similar. That's where the idea of similarity comes from. Thanks for watching. I'll see you in the next video.